Okay, so thank you everyone, and good afternoon. Thank you for the introduction, and thanks to the organizers for inviting me to this wonderful special edition. So my name is Hadrien Notarantonio. I am a third-year PhD student at INRIA-Saclay under the joint supervision of Aline Bostan, Frédéric Chizac, and Moab Safieldine, who is in Sorbonne University. And this talk will be based on two works. So the first one with Aline and Moab, and the second one with Sergei Yurkevich, who was a speaker here last year and who is also online. My area of research is computer algebra. So that is that I try to design algorithms that could solve somehow in a click some very computational difficult problems. And yeah, in this talk I'll be talking about enumerative combinatorics, functional equations, and how to solve them by using tools from computer algebra. And let me first introduce the objects that I will be interested in. So on the left, you can see rooted planar maps. So an example of such a map. You can think about planar maps as some graph which is embedded in the plane and which has an orientation given by this arrow. And on the right, you can see functional equations relating four objects, so two variables t and u, and also a function f of tu and a specialization to the value u equals 1 of this function. And well, there are things that we can say about this equation before explaining how to obtain the equation from the combinatorial problem. So first of all, observe that it writes as f is equal to a polynomial, so here a constant, 1 plus t times a big algebraic expression. And this algebraic expression, well, you can see, so the square here, it's no surprise really, but the quotient can be mysterious. And in fact, this quotient, it has a nice property, which is that it maps a formal power series in the variable t, and with polynomial coefficients in the variable u onto one other formal power series in t and with polynomial coefficients in u. And a way of seeing it is that, in fact, it just shifts the coefficient of a given formal power series f. And so in the end, you can see that there is a unique solution, which is a formal series to this equation. I'll be also interested about about bigger equations. So here you can see in this quotient that there is this red object, del f, that appears. He was not present in the last equation. And also I'll be interested about systems of such equations. And by interested and about solving such system, well, I will tell you more in a couple of minutes, but let's try to see where such enumeration problems yield such functional equations. So in order to do this, I will be interested about this functional equation that we already saw on the previous slide, but now I see it. It was written by Tott in 1968. And in the same paper, he studied this equation, and he managed to prove that the blue series, so f of t1, is an algebraic function, and also he managed to explicit a closed form expression for the coefficient of this enumeration problem. And he does this in the following way. So first of all, we define an to be the number of planar maps with n edges. And, what we usually do is to translate the given enumeration into a function. So here we take its generating function, and we try to play a bit with it, and, it's a difficult problem. So in the end, we are reduced to refine the enumeration by adding more constraints. And this is why we introduce the sequence A and D that counts planar maps with n edges, but now with D of them located on the external face. And the external face, it's like the border of the map. And algebraically, this is equivalent to introducing a new variable, u, which is often called the catalytic variable. And by considering its complete generating function, f, which is a formal power series in T and with polynomial coefficients in u. And the polynomial coefficients in u comes from the fact that you cannot have a bigger number of edges located on the border than the total number of edges. And well, from this enumeration, one observes that, well, you either have a planar map, which is a vertex, one vertex. In such a case, there exists only one such map. Or when you delete this root edge given by the arrow, then you can obtain either two disconnected maps, or you still have one connected map. And well, each of these situations gives rise to the following algebraic translations. And here the 1 over u minus 1s come from the fact that when you try to glue again your arrow on the map, then you have multiple choices for the vertices, namely the number of vertices that you have. So when you sum up, you obtain this geometric sum. And in the end, well, you glue all these informations in the following equation. And you can now study the initial generating function, which is just the specialized series f of t1. So let's try to see what I mean by studying and by solving an equation. So let me remind you that when you have a univariate formal power series in the variable t, you can have the somehow simplified version of a classification results. So you can either be the quotient of two polynomials, or you can be annihilated by a non-zero polynomial, or you can also be solution of a linear differential operator. In such a case, you're called definite. And in this talk, by solving an equation, I mean to classify the series f of t1, so that is the initial generating function, and also to compute well, a witness of this classification. And why that? Well, because, for instance, when you have the series f of t1 associated to the enumeration of planar map, then you can compute by some oracle. I will be more precise in a couple of minutes. But you can compute an annihilating polynomial, which means that when you substitute z to this series f of t1, you obtain 0. And from this polynomial r, you can deduce some properties using existing methods in order to deduce properties on the initial sequence. So now let's have a plan of the content of this talk. First, I will introduce so-called discrete differential equations, because all the equations that I've been talking about are special cases of these equations. Then I will determine the nature of the solutions of such equations, because they all have the same nature. And then I will try, well, to explain how to have an efficient algorithm that computes the witnesses of this classification. And in the end, in order, well, to see the difference with the state of the art, we will solve a problem previously out of reach. And if I have time, well, I will perform the above points for systems of discrete differential equations, and this will be the content of the work that I did with Sergei Yurkevich. So let's try to have a look at discrete differential equations. So it writes in the following form. We have a series f on the left, then a polynomial which is a constant in the variable t, and a t times an algebraic expression in some iterations, delta. And delta is what we call the discrete derivative operator, or discrete differential operator, and which maps a formal power series in t with polynomial coefficients in u, onto one other formal power series in t and with polynomial coefficients in u again, by acting on the coefficients of this series. And just to convince you that all the equations that we have been considering so far are special cases of such equations. So let's go back on three constellations. We had the following equation, and observe that we have this del u f in red. And well, it's just the second iterative of the delta operator, which is applied to a series f. And you can see it by expanding f with Taylor's formula around u equals 1. So in this case, this is a discrete differential equation of order 2, and the order is the number of times that we iterated delta. So here, k. And so what about the classification of the solutions? Well, we have a beautiful theorem due to Mireille Bousquet-Melou and Hadrien Jehanne in 2006 that implies the algebraicity of the solutions of such equations. And the striking part of their result is that the proof is constructive, which means that you have your equation, it's your input, you start their proof with your inputs, you follow all the lines, and in the end you have a non-zero annihilating polynomial. And this is very nice because it yields a first algorithm, systematic method. Let me mention that we will see a general result in commutative algebra, which is due to Popescu, and which already implied the algebraicity of the solutions in 1986. But the fact is that the result of Popescu is not effective at all. So this one for us is more interesting because we can turn it into an algorithm. Well, they turned it into an algorithm, but we can modify it in order to design new algorithms. So let's start to have a look at their algorithm. And in order to do this, I will take an example of a discrete differential equation. So here, the enumeration of 3 constellations, we remember the del f. And by the end of this slide, we shall compute the following relation between T and the series FFT1. So the first observation of Bousquet-Melou and Jehanne is that as you want a polynomial in the end, well, let's first turn it into an algebraic equation, which means that it relates algebraically f of tu, tu, and the specialized series, so FFT1 and del FFT1. We have this polynomial p. And now, well, we have polynomials. We want an algebraicity result, so let's use polynomial systems. Let's deduce a big polynomial system that admits, well, FFT1 as a solution for one of its coordinates, and then show that this polynomial system, well, the ideal spanned by these equations has dimension 0, and so we just have in the end to eliminate all variables. So let's do this. And in order to create more equations, what they observe is that they just have to take the derivative with respect to the variable u, and so by the chain rule they obtain the following equation relating the initial series. And now, well, they introduce del f, and they don't want to consider del f, obviously. So what they do is to search for solutions that somehow cancels this red term, and solution in the variable u, because in the end, as we are interested in f of t1, we don't really care about this variable u. So on this example, they show that there exist 2 distinct series, u1, u2, with non-negative exponent in t, so that we can compose them for this term, and such that there are solutions of this red term. So this is one information. But now observe that you have this green information for free. So you have the vanishing of the green term for free. And so when you duplicate your constraints, you observe that f of t ui ui f of t1 w f of t1 are a solution of the following duplicated constraints. And here there is a Rabinovich trick in order to encode the fact that u1 must be distinct from u2. Now we count the number of equations, unknowns, and parameters. So t here will be considered as a parameter, which means we put it in the base field. And now we have 7 equations and 7 unknowns. So 3 times 2, and here the saturation condition. And well, what we have to do now is just to eliminate all series but f of t1, and we preserve, of course, this parameter t. And we can do it using either resultants or in 2006, it was already mentioned the use of what we call Grabner bases that are nice generating sets of polynomial ideals. I will go back on the definition of Grabner basis in a couple of minutes, but first let's try to have some properties induced by this algorithm. So I take this polynomial system, and then I try to analyze a bit in terms of theoretical analysis, complexity analysis, what we can say about these constraints. To do this, I will first introduce some assumptions. So U1 distinct from U2, we already had it on the previous slide. And I will also assume that S has finitely many solutions, because else I cannot eliminate all variables but FFT1, all unknowns but FFT1. And I will also assume some regularity, so no multiplicity points in the solution set. And in under these assumptions, I get that there is a group action obtained by permuting U1 and U2 in these polynomial constraints. So when you permute U1 and U2, you still have a solution. So there is a group action on the solution set of these polynomial constraints. You have also the fact that, well, as the system has finitely many solutions, the number of solutions is bounded by the Bezout bound. And, well, if you apply the Bezout bound naively, you will have to take into account this condition, U1 minus U2. And in fact, the fact that the polynomial system is radical, the ideal associated is radical, this implies that you can use a variant of the Bezout theorem. It's called the Heinz-Bezout theorem, and it allows to forget this condition when bounding the number of solutions. And, well, in the end, let me present a first analysis of the algorithm of Bousquet-Melou and Jehanne. We obtain a polynomial bound in with respect to the input, so with delta as the degree of the initial polynomial equation. So this is a polynomial bound. You can see that it is of the form somehow bound to squared, and the squared comes from this duplication that we did. And also we have an algorithm here, which is in big O log. So big O log is just to say that we are hiding some polylogarithm factors in delta. So it's in delta to the 17, and observe that it is subquadratic with respect to the size of the output, to the size of the output, because we have two variables, so this is a first analysis, and as I told you, this bound, it contains the fact that we perform this duplication step. And the classical hope is that by avoiding this duplication approach, we can lower down the practical complexity. And this is what we are going to do in the next couple of slides. But first, let me remind you what is a Grabner basis. So probably many of you already know everything about it, but let's be sure. So you have a polynomial ring in the variable x and in many variables y. And I'm just saying that we can sort the monomials with some order. So here, for the first one, I'm saying that we first compare the degree in x. So 4 bigger than 3, so the first monomial is bigger than the second one. And the second order is called the block monomial order. And in case of equality, here, for the degrees in x, I'm just saying that we are looking at the monomial in y and comparing their total degrees. And in case of equality, well, there is an analogous condition to the lexicographic order. I won't enter into detail. What is important is just to say that we can sort monomials and polynomials in polynomial rings. Well, leading terms, it's the same thing. We have a polynomial. We take the biggest monomial for some order. And now a Grabner basis, it's well, a subset of a given polynomial ideal, which has a mysterious condition, which is that the ideal spanned by the leading terms of these polynomials generates the ideal spanned by all the leading terms of the polynomial in the ideal. So it might be frightening, but in the end, just remember that it's just a nice generating set of a given polynomial ideal. Such sets always exist and generate the ideal, yeah. Also, in terms of computations, difficulty, well, computing Grobner basis, it's a difficult problem, but there exist now some very efficient implementations that can somehow bypass this theoretical result. And why am I using these tools? Because Grobner bases are a very powerful tool in elimination theory. Okay, so starting from this definition, now we are going to do a bit of geometry, and very elementary geometry. So we start from the fact that we have these initial polynomial constraints, and we know that there exist two solutions, xu, with distinct u coordinates to the following polynomial constraints. And what I'm saying is that in the end, well, let's forget the x variable for a couple of minutes. What I'm saying is that when you fix the blue coordinates, there exist at least two solutions with respect to the u coordinates. And forgetting a variable is just a projection, so you project onto the u, z0, z1 coordinate space, where z0 and z1 are the variables associated to the blue series. And
may I ask,
yes, sorry.
Why is now f of t0 and the uf of t0 instead of t1?
It doesn't matter. It's because on the next slide I will use a different discrete differential equation which simplifies my purpose, but there is no, there is no big difficulty. Yeah. In the end, you just want to compute some, information about one of the specialization of your series.
It's a change of notation. It's not something really the zero of the power series.
No. Okay. The specialization doesn't matter. Thank you. And fixing the blue coordinates means that you take a point in the projection, pi u, of your projected solution set, and you are studying the cardinality of the fibers with respect to here pi u. And well, so as I told you, it's just about some cardinality condition, and let's try to visualize it with a picture. We have points alpha z on the z0 and z1 coordinate space, given by f of t0 and w f of t0. And, well, I'm just studying how many points intersect the projected set w. So I want some conditions on the fiber. So let's try to characterize this set with some polynomial constraints. In order to do this, let's take an example, a simple example. Here, indeed, I shifted the problem to some walk enumeration problem. So this is why I have f of t0 and not f of t1 anymore. And this is an equation of order 2, so I want fibers of cardinality at least 2. And as Bousquet-Melou and Jehanne did, I will go back to some polynomial equations. And as I introduce Grobner basis, I will use them. And in fact, what I will use is that you can establish links between projections, geometric projections, and elimination ideals. So ideals obtained after eliminating variables. And this is why computing a Grobner basis, so a nice generating set of this ideal for this given monomial order, in fact, characterizes almost the projection onto the z0 and z1 coordinate space. I say almost because, in fact, it characterizes the Zariski closure of the projection and not the projection itself. And we know that projections are constructible sets, but it's not always that projections are closed sets for the Zariski topology. So I'll go back on this a bit later. But now let's try to have a look at this basis, GU. It has the following form. And now we will have some very elementary observations on this Grobner basis. We know that in the end, what we want is to take a point of the projection and to lift it into at least two distinct solutions with respect to the variable u. And what we can observe is that assume that one of the polynomial in V1, so for instance, I don't know, gamma 1, we can choose another one if you want. Assume that gamma 1 is not equal to 0 at this point alpha. Then it means that beta 1 here will not be equal to 0 also. So it means that the first polynomial will have at most one solution with respect to u. And so you cannot have, for a common solution, at least 2 points in u. So what I am saying is that all the orange polynomials, beta I and gamma j, should be added to the initial generating set gu. So you force them to be 0 at the point of the projection. It's a necessary condition. And now I told you about some Zariski closure properties when you project and when you eliminate variables. And here, in order to make sure that you indeed are in the projection and not in the border of the projection somehow, then there is a famous result called the extension theorem in effective algebraic geometry, saying that if the leading term of G2 with respect to u is distinct from 0, then you indeed have a point of the projection. And so, for obvious reason, here the leading coefficient is 1, so everything is great. And now, well, it remains to have the distinctness of the solution with respect to u. And this is just obvious because you don't want the discriminant of G2 with respect to u to be equal to 0, because in this case you would have a double root. So in the end, you have a set of equations and inequations that characterize the set of interest. And this gives an algorithm because you can turn the inequations into equations using Rabinovich trick, and you can eliminate all variables except the specialized solution. And so it gives you this output. And well, just to summarize, when you don't use discriminants, when you cannot use discriminants, there is a slight generalization called Hermite quadratic forms. And in fact, the minors give condition on the number of distinct solutions of the studied polynomial G. And it's just about studying some quotient rings. So I will not go into details, just to say that we can generalize it for any other discrete differential equation. These are very elementary results that are from this very nice book that you might know. It's a reference in effective algebraic geometry called Ideals, Varieties, and Algorithms. And well, as I told you, we could derive from it a general description, and so a general algorithm. And of course, I here presented the case of order 2, but it works in the general case. And now, okay, fine, we have a new algorithm, but how do we know that it is better or more interesting than the previous one? So let's take an example, and let's try to see what we can obtain as new results. So here's the enumeration of 5 constellations that are some colored planar maps. And it induces a discrete differential equation of order 4. Using the state-of-the-art, we stopped the computations after 5 days. And in fact, using these results that I presented to you up to now, then we could compute the annihilating polynomial in less than 3 days and observe that the output is very, very small for 3 days of computations on a regular laptop. If I have time, I will show you how to decrease from 3 days to 3 hours. So I don't know if I will have time. Okay, so now a natural question is, what about systems? We have the case of one discrete differential equation, but let's try to see what we can do in the case of systems. First of all, why are we interested about systems? Well, the answer is always the same. I try to find application in my work, so I first start to do some biblio, and here there are some examples in the literature of discrete differential equations. And so this is the motivation. Again, I'll be interested about one of the specialization, either to u equals 1 or to any specific value of the base field. It doesn't matter. And now here comes somehow the striking theorem of Popescu that I was talking about. It's a very deep theorem in Artin approximation theory. And essentially, it says that when you have a set of polynomial equations that admits a formal solution, then first of all, there exists an algebraic solution to these polynomial constraints. And when you have some constraints on the variables, so for instance, if I give myself 3 variables, let's say x, y, and then a and z, and if I have, I don't know, the formal series that are series in x, assume that there are formal series in the variable x, y, and also formal series in the variable x, y, z, then under this nested condition, well, the algebraic solution given by the theorem will also have this nested condition. Okay, so now what are the applications to our framework? Well, by construction of discrete differential equations, we know that they are unique. So in fact, by the uniqueness, we obtain for free the algebraicity of the solutions. So we have the classification of the solutions, but still we don't have any algorithm because, as I said, well, up to now, it's not known to have some effective proof in the general case. Also, let's go back to an example because, let's be more precise on this nested condition. So here I take the enumeration of planar maps as we had on the first slide of this talk. And we know that there exists, well, a solution given by f and the specialized solution, f of t1. We have this nested condition. And as we have this nested condition, then there exists, of course, an algebraic series given by Popescu theorem, and with this nested condition. Yeah. So this solves partially our problem, but in the end, the problem is that we don't know how to compute witnesses, and this is somehow my goal in this talk. So I shall find a way to provide an algorithm or a method to compute these annihilating polynomials. And so what we did with Sergei was first to reprove Popescu's theorem under this specific case with only 2 variables, but in the system case and in the case of fixed point equations. So it's a very particular case, but in the framework of enumerative combinatorics, this is the type of equations that appear usually. So, of course, we have the algebraicity, but this we already had it with Popescu theorem. But now we could explicit a given number of equations and unknowns that have this specific series as one of its coordinates. And also we could prove that these equations, well, the Jacobian is invertible at the given point. And so by using the Jacobian criterion, you can deduce the algebraicity of the series of interest, and in fact of all the series. And it mainly uses some deformation techniques. So you deform your input system, you show that the deformation has some good properties, and then you show that the reduction to the usual base field is well defined and preserve the algebraicity. So let's try to see quickly how this works. Here, I already took the liberty to take the numerators of the equations that I consider, but it's quite the same as before. I have series f1, f2, and then specializations of these series. I denote now e1 and e2 to be these numerator polynomials. Before it was p. Now, well, we denoted them by e1 and e2. And we do the usual technique. We take the derivative with respect to the variable u. And instead of having some polynomial equation, we have now some matrices. We can have some somehow a linear algebra interpretation of the problem. And instead of annihilating or searching the solution of only one coefficient, here we are going to search first the solution with respect to the variable u of the determinant of this square matrix on the left. And in fact, it gives us for free the annihilation of the determinant associated to the matrix obtained by concatenating the first column and this column. Because when you have, well, this determinant which is 0, and when you have that these three columns are linked by the following relation, then you obtain for free that del x1 and del u have a relation between them. And well, the hope is that we can have an elimination procedure now. And in fact, it is completely the case because, as I told you, we have these two determinants. We set up the duplicated system as we did before for the case of Bousquet-Melou and Jehanne, so with equations of order, well, of arbitrary order, but for one single equation, sorry. It has as many equations as unknowns. And, well, we have a point of interest, and in fact, in the end, we just have to perform some elimination of variables, and this is exactly what we do. But now, observe that, in the end, the geometric setting of this system case, it's approximately the same as what we had in the case of single discrete differential equations, because, well, we have some things that are, some series that are independent of the ui's. So when we project, we have at least here two solutions, u1, u2, and so, well, all in all, it's the same geometric object. So we can generalize, in fact, the algorithm that we have with Hadrien and Moab to this system case. And so, well, now I'll first conclude, and if I have 3 minutes left, I will maybe show you how to have 3 hours of computations for a 5 constellations enumeration problem. So in this talk, we have seen some decidability results. We have used some geometry-driven algorithms for computing annihilating polynomials. And, well, we solved the enumeration of 5 constellations, but let me mention that this problem was already solved by Mireille Bousquet-Melou and Gilles Schaeffer in 2000, but by bijective proof. But here it's the first time that we can solve it in a click somehow. Also, we have a constructive proof of algebraicity of the solutions of systems of discrete differential equations. And, well, regarding the works in progress, well, as we have some algorithms, we want to make them available to the community. Then we are working with Sergey on expanding the algorithmic comparisons between all the techniques in the case of systems of discrete differential equations, because there are more techniques than in the case of one single equations. And with Mireille, we are working on the case of more nested variables, still with this fixed point nature in the equations, but yeah, trying to have a more effective understanding of Popescu's theorem. Oh yeah. Also, let me mention that there is another nice conference talking about computer algebra and functional equations in combinatorics and physics. You might be interested in this conference. It's from November the 27th to December the 11th, and it's in IHP, so in Paris. So please, if you're interested, come. And in the minutes that I have left, well, so we had, I talked to you about this 3 hours computation. So this is it. We want to have this output for the series associated to the enumeration of 5 constellations. And what I will use is some Hermite-Padé approximations. So this is what we call a guess and prove approach. First, we guess a candidate that could annihilate the series of interest. And then we need to certify that this annihilating polynomial, well, that this candidate is indeed an annihilating polynomial. And we use, in fact, the geometric bounds that we could derive with the method by Hadrien, Moab, and myself. So what are we doing is just using some genericity good properties of Grabner basis under these projections mod P in order to derive some upper bounds for a candidate that annihilates the series. And, well, all in all, this is the algorithm that we did with Hadrien and Moab, expanding the series in order to check, to do the proving step is just some Newton iteration, so very basic algorithm, but very powerful one. Hermite-Pardet approximation, well, it's a well-known tool, also in algorithmic number theory. And in the end, the certification step is just some multiplicity lemma based on elimination theory. And by applying these results, we could obtain this 2 hours and 50 minutes computations. And I'm already late, sorry. The last observation is that the bi-degrees in the output are different because here with the hybrid guess improved, this is how we call this method, we capture the minimal polynomial, while with this elimination method, we capture a multiple of this minimal polynomial. So this explains the difference in the output size. Thank you very much.
You have this acceleration by using a projection to finite fields. Mm-hmm. This could have been done in the Bousquet-Melou and Jehanne situation, or in that case you don't have this special property that you can use?
No, you can use it. And in fact, the comparisons that I am doing in the table already encapsulate these projections mod P in the implementations. So I don't know where it were. Yeah, here. It's a usual trick in effective algebraic geometry to perform the permutations mod P, apply the Chinese remainder theorem, and then lift the coefficients over the rational. And indeed, we have great timings with this duplication approach by implementing these techniques, but not enough to tackle such problems. So in the end, the geometric comprehension of the problem is really the key argument. And also, as we are talking about some implementation techniques, we also perform evaluation interpolation on the parameter T. So everything that we could do in order to compare these algorithms was done.